anything at all before we do some more stuff today? I do want to give you some practice problems. Some of them might be longer than others. The idea is just to make sure that you're familiar with them. Again, like I said, as far as the quizzes go, your quiz problems will be directly off homework problems. I'll get these listed on Moodle as well. This will take us through a couple of sections of Chapter 2 as well. We pretty much did 1.1 and 1.2 last time. I'm hoping to get at least into 2.2 today. The reason why I want to get into 2.2 today is because that actually gets us our first technique for actually solving some differential equations. We talked a lot last time about what differential equations are, what solutions look like. Oops, not 20. A little bit of when are solutions unique, but we didn't actually talk about solving some of those. And part of that, good chunk of what this class is about is actually being able to solve them. So, anyway, so these practice problems take you through section 2 of chapter 2. No, we won't go through as many sections this quickly for the whole entire semester. Just trying to get to the point where we can actually solve some things. We can go back and catch some of these other things that we've already talked about later in context. So we'll start with section 1.3 today. This is where these example problems that I gave you came out of. Mainly, they're examples of things that are like in section 1.3. Those didn't come out during 1.3. There are problems in section 1.3 that look like these. Section 1.3 is about using differential equations to model things, which is kind of the point of the class, right? You're trying to model some sort of a physical situation and then solve that particular equation. That's kind of the point of this class. We're going to focus more on the solving than the modeling pieces, but again, we want to keep sight of what we're trying to do, right? There's a reason why you're taking this class. Okay. So it's not just solving these things, because like I said, a lot of the things we're going to do in here talk about solving these things by hand. When you do these things in practice, you rarely solve them by hand, mainly because they're typically unsolvable by hand. You need to do approximation techniques. So, but you still need to know what they are, still need to know what techniques there are out there. We will do some approximation techniques as well. But again, the point of this course is learning about the techniques and a little bit about the modeling. As you go through and do more things later on in other classes, then you'll start talking about how you actually apply this to those situations. Okay. Tends to be what happens in most math classes. All right. So let's talk about 1.3. They've got lots and lots of different applications in section 1.3. We're going to talk about the ones that I have on the paper that I handed out are a specific type of a model that talks about how things, what happens as you do mixtures, and then what the concentrations look like at given times. We're only going to worry about setting these things up today because, again, we have not solved the equations yet. Okay? We haven't talked about them. After we get through section 2.3, I believe it is, we will be able to solve every problem that's on this page. Okay. However, in section 1.3, they also go through several different types of scenarios for different models of different scenarios. You've probably already talked about one before in other classes, which talks about a standard model for population growth. And I think we mentioned this the other day as well. You've got 15 bacteria. Bacteria rate doubles every hour. How many bacteria are there at time whatever t, doesn't matter what it is. Okay, that's an example of exponential growth. You can also do exponential decay in the same way. And the idea behind that particular model is that the rate of change is proportional to how much is present at a given time, right? So, for example, with a bacteria model, if I go from time 0 to time 1, we know that it goes from 15 to 30, so the change would be 15. But if you go from time 1 to time 2, if it doubles again, going from 30 to the 60, the change is 30, right? So it's proportional how much was there to begin with. So that particular model, if A represents the amount of whatever it is at time t, then you would represent that scenario as the change in the amount is proportional to the amount. That's the differential equation. This is your standard differential equation that represents either exponential growth or exponential decay. If it's exponential growth, what should k be? As far as not necessarily the number, but what kind of a number do you think k will be? It should be positive, right? Because the change should be positive, right? If it's exponential decay, it should be negative, right? So I'm guessing you've already talked about this, but you didn't write it as a differential equation. You've seen this in another class, right? You do it in algebra classes, okay? For example, you don't write it as a differential equation because you haven't talked about derivatives yet, right? But you've done exponential growth and decay, and you use this number here as your growth factor when you do your when you write down the solution. So let's think about it from a calculus perspective, though. We've got a differential equation written down. We should recognize what the solution here looks like. I'm looking for a function that, when I take its derivative, I get the function back again. Let's ignore the k for the time being. If I just said I took the derivative of the function, I get the function back again, what kind of function am I talking about? Exponential, right? Where does the k factor in? That didn't feel very good, just an elbow. Where does the k factor in? Well, when I take the derivative of an exponential, if I have a constant that pops down in front, where did that constant start out? In the power, right? Because I would use a chain rule, right? I would take the derivative of the exponential and then take the derivative of the power, so the power pops down, right? So this tells me that my solution should look like e to the kt, but I should probably have something out here in front, right? Now what should go out here in front? Well, let's think about this for a minute. The way I have it written currently, if I put 0 in for t, what do I get out for the function? 1, right? But if I said this, for example, with my bacteria example, if I had 15 bacteria at time 0 to start with, I would want 15 to come out, not 1, right? So what do you think should go here as in front? Yeah, the constant that tells you how much there is at time 0, right? And like Trey said, a lot of times we write that as A naught, right? So this gives you a general solution to this differential equation. Now, again, you've talked about this, pardon me, you've talked about this in other classes, didn't write it down as differential equations, but I also mentioned to you that in real life, if you are trying to solve differential equations, you're probably going to do it numerically. This differential equation pops up as what's referred to as a model problem, trying to talk about when you know solutions exist, or sorry, when you know that your approximations are going to be decent. Okay, we're not going to go into that much. That's more graduate level numerical analysis types of things, right? But people come back to this problem to analyze how good an algorithm is. Okay. So even though this is a very straightforward problem, it's important later on when you do more advanced approximation techniques. And I'll leave it at that, because we're not going to do those more advanced approximation techniques. Is that okay? All right. So this is the idea. When you're trying to model a situation, you're trying to write down a differential equation that explains what's going on with the change. Another one that I mentioned last time that they also mentioned in the book is kind of that the infectious disease modeling, right? You've got proportion of your population that's infected, proportion of your population that's not infected, you would expect that the rate of infections should be proportional to both groups, right? The more susceptible people that you have, the faster it should grow. It should decrease depending on how many susceptible people you have in a closed population. And they talk about that in the book. This is one I'm not going to go into too detail. But they call it, again, I mentioned this last time, the susceptible, infected, recovered model, SIR model. This is used a lot in disease modeling. If you look in the textbook on, let's see, page 24, they even talk about it a little bit there. You can change this model up slightly and do Newton's law of cooling as well. Pops out of this particular differential equation that we just wrote down. They talk about that in the book. Other things that they talk about are flow rates out of a particular tank, if you will. It depends on how much stuff is in the tank and what the opening looks like and what this area is of a particular cross section. They talk about that. I'm not going to go through that because, again, they develop it in the book. Circuits, they talk about air resistance on falling bodies. They talk about lots of different things, all right? So, again, I don't want to spend a lot of time going through all of it because you can read it, and you may have seen some of these already in other classes. You've probably seen falling bodies, for example, in another class. Pretty standard physics problem, right? Okay. Like I said, though, they do add air resistance in that as well, as opposed to, everything's in a vacuum. Everything's frictionless and everything's in a vacuum in physics, right? Okay. In any event, I do want to talk about one particular type of model because I want to go through a little bit more about what the setup looks like. So let's look at these few problems that I gave you examples here, and let's see if we can set up a differential equation. These are pretty classic mixture problems. These pop up in chemistry as well. So what we're trying to do is model the amount of a substance in a mixture at a particular point in time. That's what all of these things are trying to do. Okay. They give an example of this in the book as well, but like I said, I want to just concentrate on this one particular model because it actually illustrates what we're trying to set up here. All right. So let's talk about what's going on in this problem. We're just going to set up the equation. We haven't talked about how to solve these things yet, but hopefully by the end of the day we can solve some of these. And definitely by the end of Tuesday we should be able to solve all of them. Okay? All right. So let's just pick out what's going on. We've got a tank that has 100 gallons of fresh water. And we've got brine coming into the tank. Brine is just a fancy word for salt water, if you didn't know. Anyway, notice what it's asking in part A. It says, find the amount of salt in the tank. Okay. So we want to find a different, if we let A be the amount of salt in the tank, at time t, our goal here is to come up with a differential equation that we can solve to give us a function of t that represents that. Okay. At the end here, our goal would be to have a of t equals something. Okay, that's our goal at the end. We're going to get to that point by first setting up a differential equation, and again, that's where we're going to stop right now. Okay? All right. So, what's going on in the problem? We've got brine coming in and brine going out. Notice that's what it says. It says, brine is coming in at whatever, blah, 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 runs into the tank at a rate of 4 gallons per minute. And then the mixture kept uniform runs out at the rate of 2 gallons per minute. So we got stuff going into the tank and stuff coming out of the tank. Okay? So there's going to be a change in the amount of salt in the tank. Right? We've got salt coming in through the brine that's coming in at a fixed amount of salt per minute. And then we've got brine that's going out of the tank, but that brine is changing, right, over time because you got stuff coming in to a tank that originally had some fresh water in it, right? Okay. But simple concept as far as the differential equation that we're going to use. If A is the amount of salt and T is the time, we want the change in salt over time that's in the tank, right? Well, we got salt coming in, salt going out. We're just going to set up a simple subtraction. We'll have rate in minus rate out. Simple concept, right? We got salt coming in, salt coming out. We know how fast the salt comes in. We can come up with an expression that represents how fast the salt goes out. Right? All right. So let's do the easy part first. Let's do rate of salt in. 2 pounds per gallon, 4 gallons per minute, right? Now let's think about units. Many of you are science students, so you think about dimensional analysis types of things, right? Let's look at the left-hand side of the equation. A represents amount of salt. T represents time. So if I'm looking at dA dt, what are the units on the left-hand side? Pounds per minute, right? So another reason why we like Leibniz notation, it's suggestive, which doesn't mean it's dirty, right? It's a suggestive notation. It's written as a fraction, so it tells you things look like fractions, right? Units on top is pounds, units on bottom is minutes, so it should be pounds per minute on the units on the left-hand side. It's one of the reasons why we like Leibniz notation, even though a lot of times it's ugly, right? Okay. All right, so if I have pounds per minute on the left-hand side, I better have pounds per minute on the right-hand side. Okay, so brine comes in at 2 pounds per gallon at 4 gallons per minute. How can I get pounds per minute out of that? Multiply them, right? 2 pounds per gallon times 4 gallons per minute gives me what I want for the rate in, doesn't it? Yeah. Okay. That part's relatively straightforward. Why is that relatively straightforward? Because the brine is coming in at a fixed concentration, right? We know it's 2 pounds per gallon, right? The second part's a little bit more difficult. I got to figure out actually 2 things, right? One, I need to figure out, pardon me, we know how fast things are going out. That's not the harder part. But I need to figure out the concentration of salt in the tank at a particular time, right? Notice that I've got a concentration of salt with the 2 pounds per gallon, don't I? So I've got concentration times rate, right? So I need to do the same thing for the rate out. I need a concentration times the rate out. Well, it's coming in at 4 gallons per minute. How fast is it going out? 2, right? Okay. So I know that the second part is going to be 2 gallons per minute. The part that I need here needs to match up kind of with the part here, doesn't it? This was a concentration of salt in the tank. It needs to be something as pounds per gallon, right? Do I know how many pounds are in the salt? Excuse me, how many pounds of salt are in the tank at time t? No, that's what we're trying to figure out, isn't it? I literally wrote, let A equal amount of salt at time t, right? So I don't know how much salt is in the tank, right? If I knew how much salt is in the tank, I could divide it by the gallons, and that would give me concentration, right? So on the top, I'll just write A. To get concentration, what do I need to know? How am I going to get a concentration? What do I need to divide the amount by? Gallons at time t, right? All right. This is a little bit harder. I agree. It's a little bit harder because I got to get, well, yeah, it's always harder. Is the amount of stuff in the tank constant? No. Stuff is coming in faster than stuff is going out, right? So I'm going to have an expression that's going to have a t in it, in the denominator, right? Because the amount of stuff in the tank is changing as time goes on, right? So what expression is going to be in the denominator, do you think? The rate in, okay. It's going to involve the rate in, I agree. So it's a little bit more than just that. Let me ask you this. If I knew that there was, I know it says it was fresh water, but ignore that for the time being. If I knew that there was 5 pounds of salt in the tank initially, what would the concentration be? How would you find it? If there's 5, initially, how much stuff's in the tank? 100 gallons. If I said initially there were 5 pounds of salt in the tank, what would you do to find the concentration? Yeah, divide 5 by 100, right? Okay. What if I said rather than initially, what if I knew that there was 5 pounds of salt in the tank after 1 minute in this setup? What would you divide by? How much stuff is in the tank after 1 minute? Close. Not quite 104. Because stuff's going in and stuff is going out. It's 102, right? Because what's happening? 4 gallons of stuff came in, but 2 gallons of stuff went out, right? So after 1 minute, there's 102 gallons, right? What if I said that there was 5 pounds of salt at time 2? What would I divide by? $104, because it went up another 2 gallons, right? Time 3, you would divide by 106, 108, and so on. Can I come up with an expression in terms of t to represent that? What are you adding for each value of t? 2 gallons, so what would it look like? Yeah, okay, 2t, right? So the denominator here should be, it started at 100 gallons, and then you add 2 gallons every minute. So if we set this up, dA dt equals 8 minus, I can actually factor a 2 out of the denominator and cancel. So you would have A over 50 plus t. That would be our setup in this case. Okay, so this would be our differential equation. Let me ask you, what order is this differential equation? First, all right? First order differential equation. Okay. Pardon me. Is it linear? Yes. Because why? Nothing's happened to the A. Fantastic. That's exactly right. Remember, for a linear differential equation, your dependent variable, whatever is involving the dependent variable, can't be inside any function, right? And they can't be multiplied together. Okay? And like Trey said, nothing's happened to the A. I have a dA dt and I have an A, right? Doesn't matter there's a t in the denominator, that doesn't matter. Okay? T is the independent variable here. So this is a first order linear differential equation. And we'll talk about how we solve that type of differential equation probably Tuesday. I'll put it today. Might. Depends on how quickly we go. But we will be able to solve this later. And by later, I mean at least by Tuesday, okay? If not today. All right. So it's a first order linear differential equation. So this is kind of the point of this class, is to pattern recognize, right? I recognize this as a specific type of differential equation, and we are going to have one hammer to hit this differential equation with. We will have exactly one way to solve this. Okay? I have this nail, I'm going to grab this hammer. Maybe screws are a better example. All right. All right. One more thing about this problem before we try to set it up. You'll probably want to see one more example, I'm guessing at this point. Okay. One more thing. I want to set this up as an initial value problem. Okay. Notice that the problem asks you how much salt is in the tank after 20 minutes, I think, or whatever that says. They pretend that this is 120 gallons. But whatever it's asking you for, it says, what is the amount of salt, right? To figure out an exact function, I need an initial value, right? Agreed? Okay. So remember, A is representing the amount of salt at time t. Is there information in the problem that tells you an initial amount of salt? What tells you the initial amount of salt? It's fresh water, right? If it's fresh water, how much salt's in the tank at time t, at time 0? 0. Good. So your initial condition here, pardon me. Your initial condition here would be A of 0 equals 0. And we've set it up. Now, once you've got it set up, you would solve the equation and then be able to answer the questions. So far, so good? All right. The well-mixed part, by the way, was kept uniform by mixing, is allowing us to put in that part there. If it wasn't uniform, you wouldn't have that concentration spread out throughout the entire tank. So the uniform part's telling you that part that I put in the box. This actually is a pretty good example of what you have to do in modeling. You have to make some assumptions. Whether or not those assumptions are valid is up for debate, depending on the situation. Okay? This is an assumption that's being made that since the mixture is kept well mixed, I can assume that the amount of salt in the tank has been uniformly distributed throughout the entire tank. So the same amount of salt would be coming out wherever it's leaking from, or purposely either leaking or the valve is open. Does that make sense? All right. Let's look at the next one. This one, you've got some sodium nitrite coming in rather than salt. It's the same concept. Okay. So the 100-gallon mixing vat is initially half full of water. Does that part, by the way, tell you anything about the, what does that tell you about when it says pure water? It just tells you the initial condition, right? The half full is important because we have 50 gallons of stuff to start with, not 100, right? Okay. So in this example, same setup. Let's let A be the amount, in this case, of sodium nitrite. In the tank at time t. We've got 2 gallons of stuff coming in and 1 gallon of stuff going out. Again, exact same concept that we just did a minute ago. We're going to do rate in minus rate out. The stuff coming in is going to increase the amount of sodium nitrite. The stuff going out is going to decrease the amount of sodium nitrite. This is the fundamental concept for this type of problem. Rate in minus rate out. Really straightforward as far as that goes. All right. Again, notice that the problems are given to you in terms of concentrations and then changes in volumes, right? Keep in mind what the units are on the left-hand side. This is, I forgot what the units were. Pounds. I think it was pounds per gallon. It's pounds per minute. Yeah. All right. So what does your rate in look like? Yeah, 1 pound per gallon times 2 gallons per minute. Good. I remember when I was an undergraduate taking physics, I never memorized the formulas. I just memorized all what the units needed to be and came up with the formulas that way. Didn't bother ever remembering a single formula. I just remember I knew what the units were. And, okay, how do I combine the numbers in the problem to give me the unit that I need? Poof, that was the right answer. Hey, shockingly enough. All right. Rate out. I still need to do the same concept, right? I'm going to write it as units to start with. I need to do pounds per gallon times gallons per minute. And it's a matter of filling in blanks here, right? Gallons per minute should be relatively easy. How fast is stuff going out? 1 gallon per minute. Good. That part should be the easier of the two that you need to fill out, right? Because it's going to tell you how much stuff is going out at a given time. The harder part is what goes in the next piece. Pounds per gallon of the well-mixed curing solution, right? How many pounds are present at time t? Well, at time 0, it's 0, right? But at any given time t, what do we represent it with? In the A, right? So the numerator here needs to be A. What are we going to divide that by in this case? Yeah, it'd be 50. Good. 50 was the initial amount of stuff in the tank, and it goes up by 1 each minute, right? Oops. Try that again. That was just a 1. I said 1, and so I wrote 1. Goes up by 1 each minute, so it's 50 plus 1t. Right? And so if I simplify, that looks a lot like the previous problem. A lot like the previous problem. That okay? You can see where this might be a model that you could apply to drug concentration in a bloodstream. If you've got an IV drip going in, for example, right? You know how much drug was in the bloodstream to start with? Hopefully none. And you've got a concentration of the drug going into the bloodstream, and you want to have a constant level of the drug to fight the infection, say, or you just have saline going in because you're trying to keep a patient stable, what have you, right? You can see that this would be something that people might want to know in medicine. Same kind of idea. Lots of different applications to a relatively simple problem. I say relatively simple. These are not necessarily simple themselves. It's just they're not overly complicated setups to get to it, is what I mean. That's okay? That's what every one of these problems is going to look like, by the way. Like I said, they have other examples in the book. Most of them they've already developed the formulas for you, so you just need to plug in the numbers to get things set up. This is why I'm not doing them. They literally go through the setup in the book. Just wanted to give you a taste of what's going on. And we will get more tastes as we go along later. This was, again, first order linear differential equation. You can probably imagine scenarios where you might be able to set up equations that involve second order. For example, if you've got a falling body, Falling bodies depend on acceleration. Acceleration is the second derivative, so you'd be setting up two second order differential equations for those. Or if you've got something with forces, forces mass times acceleration, you're going to set up something with a second derivative. Spring problems, for example, you get a second order differential equation pop up. We'll look at those later. We'll do some examples of those. Okay. Any questions on either of those two examples? Not horrible, right? All right. Let's go into starting to solve some ideas, some things. Before we do some solving, we're going to do some representing and looking at some approximation ideas. So in chapter 2, the first thing they talk about, the section 2.1 says solution curves without a solution. All right. So the first thing that they want to do in this particular section is visualize what's going on with the differential equation. And then if you're given an initial condition, what does the solution have to look like? Rather than me try to draw a bunch of things and you try to create things by hand, there are lots of different generators out there for what we're going to do. So I found a good one, and I'm not going to reinvent the wheel. I'm just not. All right. This particular website generates what are referred to as slope fields. So here's an example of a slope field. They've got examples of pictures in your book. So let me just go through the different pieces. And like I said, rather than us trying to draw them all out by hand, let's use technology. You're going to use technology on these anyway. You're never going to try to draw these out by hand. That's a stupid waste of time. Okay? But it is important to understand what the technology is telling you. So at the top, they give you ODE, just stands for ordinary differential equation. So that's all the O part is. It just means you have one function of one variable. If you've got one function of several variables, you're going to be talking about PDEs, partial differential equations. Okay. So the O is just ordinary, which is what we're going to do all semester. All right. So they give you the differential equation dy dx equals x plus y. Okay. First order, and it's also linear because the y and the dy dx are just standalone, right? Nothing's happened to either of them. Okay. This actually is number 6 in your text. I mean, this was the example the person made for the website, but this is number 6 in your text. Okay, in section 2.1. All right. What is going on here? Well, remember that the differential equation is telling you what the change in the function is based on the x value and the y value. Okay? So let's see what's going on in this case. Right about here is the point 1, 1, right? If I have x is equal to 1 and y is equal to 1, then it says dy dx should be 2. Let's plug in 1, 1 there, right? Okay. Which means that the slope of this little line at the point 1, 1 should be 2. That's all it's doing. It's just graphing tangent lines. Tiny little tangent lines, right? Because again, if I change my x or change my y a little bit, the slope's going to change. Okay? So that's why it's tiny little tangent lines. When should this be equal to? When should you see horizontal tangent lines? Let's do that. When should you see horizontal tangent lines on your picture? You can look at the picture or think about the problem. What is the slope of a horizontal tangent line? 0. So we're looking for when the derivative is equal to 0. What has to be true if your derivative is equal to 0? If dy dx equals 0, what has to be true? Yeah, the y is negative x, right? They're equal but opposite, right? Equal in magnitude but opposite of each other. So if I look along the line y equals negative x, which is this way, I should be seeing things that are horizontal. Now, depending on where these things got plotted, you can't really see it. But notice here, I can see at the origin it looks like it's going to be pretty flat there, right? Because I've got one that's flat but negative, and then one flat but positive. This is going to be flat but zero somewhere in between, right? So I should be following that line. They should be pretty flat, right? All right, so you can see those different scenarios here. The whole point of this, though, is to, okay, this is what it looks like overall. If I have an initial condition given to me, what should the solution look like graphically? We're not going to have an exact solution here. It's going to be graphically. So, for example, if I had the initial condition, say I want to start right here, am I going to go up? Remember, these are giving you, should be the slopes of the function, right? So if I start right here, am I going to go up? Am I going to go this way? No, I have to follow the slopes, right? So if I start, say, right here, I'm going to follow this slope, it goes this way, and just keep following the slope as I draw it, right? If I start up here, it'll start, and then it'll turn, and then it should go back up, right? And then following the slopes. Let's see if that actually is what's going on here. Whoever wrote this allows you to just click a point and it'll draw the curve from that point. Okay? So we said if I start down here in this area, it should continue down, right? So let me just click. There it is. Notice it went down this way, right? I said if I clicked up here, it should go down for a bit and then go up, right? Sure did, right? Okay. Same idea, no matter if I start here or on this side of this line. Notice this line's got something special going on here, right? If I click above it, it's turning upward. If I click below it, it's going downward. All right. In any event, that's what a slope field does. Okay? Sometimes these are called direction fields. Direction field, slope field, same thing. So the idea behind this is you're given the differential equation. You sketch out these slopes. And by you sketch out these slopes, I mean you put it into something that'll sketch the slopes for you. Okay? You're not going to do this by hand. It's stupid to do it by hand. Okay? And then that tells you an idea of, okay, if my initial condition is here, I draw it this way. If my initial is down here, I'll draw it this way. Okay. Let's do another example. This is number 10 in your text. What's nice about this one is I can just go in here and I can change the function. So in number 10 in your text, the differential equation is dy dx equals x times e to the y. I don't know if I can type in e caret y here and it'll know what to do, but I know that exp of y works because I did it in my office earlier. All right, so this is the differential equation. Before I hit enter, let's think about what this might look like as the slope field. Okay. Is e to the y ever negative? No, it's always positive, right? So if I am to the right of the y-axis, meaning my x's are positive, should I see my slopes going this way or this way? So this way, right? They should be going up, right? Okay. If I'm to the left of the x-axis, it should be going the other way because my x will be negative, right? My e to the y is never negative, so my x is going to tell me if I'm going up or down, right? Now let's go the other way. As I get my y's being bigger, should my slopes be getting steeper or should they be getting flatter? If my y gets bigger, should the slopes get steeper or flatter? They should be steeper, right? The bigger y gets, the bigger e to the x, e to the y gets, right? So down here, when I've got negative y's, I should be seeing things that are positive but flat-ish, right? But as I move up, they should be getting more and more positive and getting steep, right? Over here, they should be negative but flat. And as I go up, I'm going to have to change that arm. I can't bend the arm the other way. They should be getting more and more steep as I go up, right? That's what it should look like. And this is the kind of analysis that you should be able to do if I want to type it in, right? Because again, technology is great, but you need to make sure what it's giving you makes sense, okay? So if I hit enter, it kept the solutions, the curves in there. That's exactly what happened, right? Down here, they're flat. As I move up, they get steeper. Down here, they're flat. As I move up, they get steeper. To the left of the to the left of the y-axis, they're negative. To the right of the y-axis, they're positive. That's what the slope looks like. What the slope field looks like. And again, it keeps the solution curves in there. To me, I think I could just refresh the page before I did it, and then I got rid of the solution curve. I haven't played with it enough to see if I can get rid of the curves on there. Okay. But anyway, it makes sense that all of these should look the same way, right? Because again, if I think about drawing it, I'm going to follow the slopes. Comes down, they're going to get flat, and then it's going to go back up again. Does that make sense? That's what slope fields are. Let me refresh it and see if we can do one more. This is number 12 in your text. 1 minus y over x. All right, so again, let's think about some properties this slope field should have when I hit enter. May not have a sense of what's going to go on overall, but we should have an idea of what's going to look like when I hit enter, so that I know that I've typed it in correctly, as opposed to typing it incorrectly. I'm sorry, bad joke. That's what I do. I tell lots of bad jokes. It's fine. Okay. All right. Anyway, let me ask you this question. What should happen at the y-axis? Start there. What should happen at the y-axis? What's the x value at the y-axis? 0. So what's going to happen? Yeah, you get it undefined, right? It's going to be a vertical slope, right? Agree? Okay. So if, well, this will be another piece that we'll do here in a minute. If I click a solution over here as an initial condition, should it ever cross to this side? No. We're going to get an asymptote of some sort there, right? Yeah. What happens at the x-axis? What are your slopes going to be all the time? 1, right? If we're on the x-axis, the y is 0. So when I draw the slope field, it should have a bunch of slope 1 lines going across. What needs to happen to make the slope 0? Y over x is 1 or y equals x, right? So along the line y equals x, I should be seeing flat slopes, right? Okay, let's see what happens when I hit enter. You said, let me see if I can make this go away. You said that as we get close to the y-axis, we should be seeing an asymptote idea, right? Which we do. Okay. As we go along the y-axis, I see the constant slopes of 1. And as we go along the line y equals x, which should be this way, I should be seeing horizontal tangents. The scale is not great, right? Because my x scale is that big, and we can kind of see it this way. right? Okay. So let's click some initial conditions. One of the ones that's in your text says y of negative 1/2, so negative 1/2 is here, is equal to 2, which is up here. And I don't know if I can scroll it or not. Nope, I can't. Oops. Oh, well. Ignore that one. Notice again, it's going to go up, and it's not crossing the y-axis, right? On the next one, if we had y of 3/2 is 0, which is about here. Same idea. And then if we clicked a couple other ones, if I click this one here, we should have something that goes down and goes back up again. Now go back up again. Notice these are hyperbolas, by the way, rotated hyperbolas. Questions on that at all? Okay. Literally, that's all we're doing here with slope fields. That's it. All right. So the other part that they talk about in this particular section is what's referred to as autonomous first-order differential equations. But again, the idea behind these autonomous differential equations is just to get an idea of what solutions need to look like. And I'll go back to the slope field generator here in a minute as well to help illustrate some things that are going on. But all we need, remember that one of the things that we said that we did with the differential equations was kind of write it in that normal form, where you had the highest order derivative on the left-hand side, and then to put everything else on the right-hand side, right? When it's autonomous, what this means is that your independent variable does not show up explicitly in the differential equation. That's all autonomous means. There's no explicit reference to the independent variable. Okay. So, if I think about it as y's and x's or y's and t's, and write it in that normal form, if it's first order, then my dy dx or my dy dt or what have you is just a function of y. It's equal to a function of y. There's no x there. That's what autonomous means. Your exponential growth and decay differential equation we came up with earlier is an example of an autonomous differential equation. Okay. The mixture problems, both of the mixture problems that we did before, are not autonomous because the t popped up. Right? If you had a mixture problem where stuff coming in and stuff going out was at the same rate, then t wouldn't pop up and that would be autonomous. Okay? All right. So autonomous just means if I have dy dx, there's no x's anywhere else. Okay? You can have autonomous second order or autonomous third order or what have you. Again, in those, x just doesn't appear explicitly. Okay? If it's a third order autonomous, you would have a y triple prime, a y double prime, a y prime, and a y. That's all okay, but no x's. Okay? All right. Why do we care? Okay. Let's look at a slope field, and then we can talk about some things about the individual solutions. So let me go back over here real quick. Put the keyboard back on so I can actually type, because that helps. This is number, let's do 24 in your text. All right. Now let me refresh it so the solution curves are off there. Sorry. 10 minus or excuse me, plus 3y minus y squared. All right. So first thing I want to notice here, this isn't, might not be the greatest example. That's okay. We're going to deal with it. Notice that this is autonomous. So as we move from left to right, those slope pieces on those same vertical lines all look the same. Or I'm sorry, on different vertical lines all look the same as you go up, right? It looks the same here, 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 and so on down the line. Okay? All right. If I had a solution where the initial value for whatever x, doesn't matter, the initial value for y was -2, what would happen to that solution? What would happen? If the initial value for y, didn't matter where the x is, what would happen? It would be a straight, horizontal line across, right? It wouldn't move because at x equal to -2, you can check, or excuse me, try that again. At y equal to -2, you can check dy dt or dy dx is 0, right? So if the change is 0, you're never going to move off that line. Okay? We call that a steady state solution or an equilibrium. Right? So it would have an equilibrium at -2. Because I haven't played enough with this yet to know what I can change or not. Let's try the settings button. Oh, wonderful. Let's do -8 to 8. There we go. Cool. All right. Do you see another equilibrium? We said there was one down at -2. Do you see another one? Y equals 5, right? And again, you can check if you plug 5 in there. All right. So those are equilibria. All right. There's one at -5. Excuse me. One at -2. One at +5. What happens if we start trying to graph some of these solutions? If we had different initial conditions and wanted to graph some of these. Okay, so here's my equilibrium. If I started over here, would I get closer to the equilibrium or farther away? Farther away, it would go down, right? If I started up here, would I get closer to this equilibrium or farther away? Farther away, right? So equilibrium means if I start there, I stay there. But what would happen if we move it just a tiny little bit? Does it stay there anymore? No, it flies away, right? So that type of equilibrium is what's referred to as unstable. Okay? If I move a little bit, right? Perturb it up, perturb it down, it moves way away from the equilibrium, right? It's kind of like maybe you've got a bowl and you've got a ball bearing. You set it right on the top of the bowl, it doesn't move, right? But if I touch the ball bearing, what's going to happen? Roll off, right? Versus if I have the ball the other way around, the bowl the other way around, and put a ball bearing in the bottom of the bowl, if I push it, what's going to happen? Right back to where it started, right? So notice that's what happens in the other one, doesn't it? If I start up here, this is my equilibrium, if I start up here, I get closer. If I start down here, I get closer. Okay? All right. So this type of equilibrium is referred to as unstable. If I move off the equilibrium, I go away from the equilibrium. If I start at this equilibrium and move off of it either way and go back to it, that's referred to as stable. We also have ones that are referred to as semi-stable. I'll see if I can put an example of a semi-stable one up here. Let's look. This is number 22. It's y squared minus y cubed. And I need to change this. It's hard to see. Let me make this 1.5. 1.5. It's kind of hard to see what the semi-stable is here. If I look at y squared minus y cubed, you should see that we have two equilibria. Y squared minus y cubed is 0 when y is 0 or y is 1. Pretty easy to solve, right? Just have equal to 0 and solve. Okay. I see that the equilibrium, looking at the picture, I see that my equilibrium at 1 is stable, right? Here's my equilibrium at 1. If I'm above it, I come back down. If I'm below it, I go back up. So 1 is stable, right? Look at 0. If I'm at 0, I move down, I come back up, right? So it goes back to it. But if I move up, it's kind of hard to see, but notice that all these slopes are actually positive, aren't they? So I wouldn't move back down, I would go up. So it doesn't come back to it. So we refer to that as semi-stable. Okay. All right. So if I didn't have the slope field, how would we analyze this? So let's do number 26 in your text without doing a slope field. Not that you can't do a slope field to check your answers, but let's look at number 26. They give you dy dx equals y times 2 minus y times 4 minus y. Again, to find the equilibria, you're looking for when the derivative is 0. When is the derivative 0? What values of y make the derivative 0? Yeah, y is 0 and 2 and 4. Good. So the equilibria here and these are solutions, right? These values would work. They're equilibrium solutions. Y equals 0 works. Y equals 2 works. Y equals 4 works. Those give you actual honest-to-goodness solutions, right? What we're going to create out of this is what's referred to as a phase portrait, if you will. That's what the name of it. All right, so what we're going to do here is just put in a couple of dashed lines at the equilibrium solutions. And it's a little harder to put in a dashed line when I've got the x-axis there, but that's okay. And we're going to think about what happens if we move off of these equilibrium lines, okay? And just draw a general solution, okay, somewhere. The book shows these general solutions typically on, like, off the y-axis. Doesn't really matter where you start, okay? But let's say you had a solution that started down here. That would be your initial condition, okay? Which way is it going to go? All right, well, we're less than 0. And you've done problems like this when you've taken calculus, doing increasing and decreasing, or concave up and concave down. It's the exact same concept, okay? Pick a test point. Pick a number less than 0. -1. Fantastic. If I put -1 in for y, I get negative times positive, right? Makes it negative, right? So if you've got a solution down here, am I going to draw it up or down? Down, yeah. It's going to go something like that, right? That would be a general solution. Agreed? All right. We're going to do 3 more. But let me ask you first, is 0 stable? Is the equilibrium y equals 0 stable? No. I don't know that it's unstable yet, but from that picture, I know it's not stable, right? Because the graph didn't go back up to it. Okay. All right. How about here? Same idea. Pick a test point. between 0 and 2? 1. Is your derivative positive or negative? And put in 1 for y. Yeah, this would be 1 times 1 times 3 is positive, right? Now, again, you're not going to cross over your equilibrium solution, right? Because those slopes are going to get really, really flat. You're not going to cross it, just like we didn't cross that horizontal asymptote, or excuse me, that vertical asymptote earlier. So when I draw a graph like this, it's going to go up. It has to have a positive slope all the time, right? So now you should be able to answer the question, what kind of equilibrium is y equal to 0? Is it stable, is it semi-stable, or is it unstable? Unstable, right? Good. Because both directions it flew away from the equilibrium. Okay. Now do the last two. If I have y equals 3, is dy dt positive or negative? Negative, so we'll come down. So y equals 2 now is what? Stable, good. Last one, if I pick something bigger than 4, get positive, right? And so we'll go up, and so then y equals 4 is unstable. You've probably noticed, or if you think about it a little bit more, you will notice that in order to be semi-stable, I better have a square on something, or a fourth power, or something along those lines, right? It better be an even power that's giving me the 0. Yeah, negative times negative. Yeah, it's easy to do. You can actually, you can just plug them in. I was just looking at the multiplication. Is this okay? All right. All right, so that's all of section 1, by the way. So let's start section 2, because we got about 7 minutes. Might as well take advantage of the time. Oops, that's not how you spell separable. Separable. We're going to start with our discussion about how to solve certain differential equations. All right. I'm going to do this with an example to start with, and then we'll do some definitions from it. This is number 6 in section 2.2. I'm going to write it slightly differently. I'm going to write it as dy dx equals negative 2xy squared. All right, so we've got written this in that normal form, right? We've solved it for dy dx. This type of equation is what's referred to as a separable equation. What makes it separable? Well, what makes an equation separable is if, when I write it in the normal form, I can basically factor the right-hand side. And I have to be able to factor it in a special way. I need to be able to factor it as function of only x times function of only y. Okay. It has to be function of x with no y's times function of y with no x's. Okay? Which I can do here pretty straightforwardly, right? Just put parentheses to see it, right? Function of x, no y's, function of y, no x, right? So your book typically writes it like f of x times g of y. Now, if you have x plus y, is that going to be separable? No. Okay? Because it can't be function of x times function of y, right? It has to be multiplied. Okay? All right. This is a really, if it's separable, this is a really straightforward way to solve the differential equation. Because all we're going to do is we're going to rewrite the equation in an equivalent differential form. Remember, back in Calc 1, we had this idea for our derivative, right? But we also said in equivalent differential form, I can write it this way. That's the differential, right? But they say the same thing. Okay? All right? So what we're going to do is we're going to write this in an equivalent differential form, but we're going to take all of the y's and put them together, and all of the x's and put them together. Okay? So I'm going to write this as 1 over y squared dy, and I'm going to write it as negative 2x dx. Now, when you do this, you're not going to have a dy in the denominator, you're not going to have a dx in the denominator. Okay? I need function of y dy equals function of x dx for it to be separable. Okay? Don't try to get creative with the differentials. Okay? Basically, with the differential piece, it looks like that we're multiplying both sides by dx, but really we're just writing it in equivalent differential form. Okay? All right. Why do we write it this way? Well, remember, we're thinking about y as a function of x, right? What this left-hand side, even though it says y squared dy, 1 over y squared dy, really we're integrating with respect to x, but we've done something that looks like a u substitution. Remember when you did u substitution? Right? You took out your x's and put in u's and got rid of all the references to u or x and put them all with the u's and then integrated with respect to u. It's kind of what we've done on the left-hand side here. We've removed all references of x's and replaced them with y's. So I'm going to integrate both sides with respect to x, but on the left-hand side, it's really like we're integrating with respect to y because we've done that u substitution, right? Y substitution in this case, right? That's a lot of words to say. You're going to integrate with both sides, okay? Integrate with respect to y on the left, integrate with respect to x on the right. That sounds like you're cheating, but you're really integrating both sides with respect to x because y is a function of x, okay? But we've done a substitution where we've written in terms of a different variable, okay? We're not cheating, it just looks like we're cheating, okay? If you don't want to worry about the technical detail, don't. Just be able to do it, okay? But we're really not cheating here. I know it kind of seems like magic. Okay. All right, now integrate. That's y to the negative 2. Antiderivative for y to the negative 2 is what? Yeah, negative 1 over y, negative y to the negative 1. Integral of negative 2x squared, negative 2x will just give me negative x squared plus a constant, right? Technically, I would have one constant on the left and one constant on the right, but then I could just move the constants together and combine them into one. Yeah? Okay. A lot of times we'll solve this for y. Sometimes we can't solve it for y, but sometimes we can. Okay, this one we can, right? Multiply both sides by negative 1 and then reciprocate. Okay? Y equals 1 over x squared plus c. Now notice I said multiply both sides by negative 1. When I multiply both sides by negative 1, I can think about the c as absorbing the negative, which is why I left it as a plus sign. But when I flip it, I have to leave it as plus c in the denominator, right? Because fractions don't split up over sums in the denominator. There's the solution. There's the general solution. If we had an initial condition, we could figure out what c is. If you can't solve for y because it's just not possible to solve for y, then you just leave it as a relation. And don't bother solving for y. This one I could solve for y, so I did. That's it. That's what separable differential equations are. The hard part is determining on whether or not you can separate it. And then how hard the integral is. But the hard part is whether or not you can separate it. Okay. It's okay? We'll do more of these on Tuesday, as well as get into linear differential equations, which is section 2.3. Okay. All right. Have a good weekend. See you on Tuesday. Some of you will see in about 15 minutes. But everybody's so quiet. Have a good one. I'll be right back. I need to stop my